Looks like we're recording. Okay, so welcome everyone. So today is a Realm week. So what I want to cover today is talking about index spaces, and in particular their implementation using Sparsity maps in Realm. So what we're going to do is talk about how index spaces work, and then how you compute sparsity maps, and give some examples of that. We're not going to show all the examples of how you make sparsity maps and stuff like that and how they work. But I will talk about some of the at least a few of the more basic ways to do that. We'll have to get into some of the more interesting ones in a later Realm session. Okay, so to start off with, so I'm in the index-space.h header file here for Realm, and one of the interesting things that Realm does is that it actually wants to understand the geometry of your data. And this is something that's pretty unique to Realm and Legion, is that we actually data tends to have structure to it, especially when it's either dense or sparse. And unlike things that want to just treat data, unlike most systems that want to just treat data as blobs of bytes that you can copy around and chop up and stuff like that, Realm actually wants to understand the structure of that data. In particular, there is a I forget that Sean puts all the annotators in the public API annotations on things here. Let's see. Or actually, I think point is a separate class. Let me actually open that up. Yeah, so actually, I should have pulled this over here, but we actually have classes for representing data, right? So there's like a point class to represent a point of in an index space. These are all nice and templated, and you'll see all the public annotation APIs, which are why I was having trouble finding stuff. But we also have rectangles, and these rectangles are n-dimensional, right? So they represent, sort of concave, rectilinear sets of points in an index space. And they're represented, in the way that you might expect. Let's see, there's a high and a low member variable on each of these rectangles. Let's see if I can find it here with all the annotations. Yep. So there's a point that represents the low point in the rectangle, and a point that represents the high point, and so you can very, very compactly represent, a bunch of points inside of an index space, right? And so when we go to look at the actual index space class here, select for class Realm public API index space. This is index space generic here. The actual index space class is, let's see, where is the actual index space class? Here it is. Right, so the actual index space class, right, is a plain old data type, right, that has a rectangle that describes the set of points inside of it, right? And for anything that's just a dense rectangle, right, an index space that represents just a dense rectangle of points, that's all you'll have in here. This sparsity map thing will be will point to 0, which is effectively the no sparsity map, saying there is no sparsity data for this index space. It is a dense set of points, and you can copy it around by value and do all the other kinds of things that you might want to do on it, like test whether it's dense or empty, or whether it overlaps with another index space, or what its volume is, like how many points are inside of that index space. There's all sorts of tests and things that you can do with index spaces that we'll get into, over the course of many of these talks. But effectively, an index space is just a collection of points, and if you can represent it compactly, we do represent this compactly. But in the case where you actually have, sort of a collection of points which cannot be represented compactly as a single rectangle, right, then we will have a sparsity map. And that sparsity map is going to be the thing that describes the set of points inside of this index space in a way that, is somewhat efficient, but can deal with like irregular and, convex shapes, and having holes in the middle of things, and all sorts of other interesting patterns in your data. Importantly, this bounds is still valid even when you have a sparsity map. And this bounds actually gives you an upper bound on all of the points inside of the sparsity map. And we'll actually see some cases where we actually use that. Now, an index space, as it alludes to here, is a plain old data type, which means that clients can copy these things around by value, right? So you can serialize them up inside of a message or any other kind of any other kind of buffer that you might need to pass from one node to another, and then you can unpack it on the remote side and refer to that, to this index space on that remote node, right? And so you'll notice this index space has no default constructor, or actually has a default constructor, but it's still a trivial type. There's no copy constructor, no operator equals, so all these things can be copied by value and passed around without Realm being aware of the index space being passed around. Okay, so the interesting thing, in that sense, index spaces are incredibly simple. They just have this rectangle bounds, and they've got a pointer to a sparsity map. But the interesting thing is, when you actually have a sparsity map, how does that actually work? How do you make those things? How do you compute them? And so in particular, what I want to look at a little bit first is how the sparsity map, what this data structure actually represents and what its structure is. And then what we're going to do is actually look through one of the things that you can do with Realm index spaces is you can actually compute an intersection between two index spaces, right? So this is a static member function on an index space, right? And it can take two index spaces and compute an intersection between them and give you back a new index space result. And give you some profiling results if you ask for them and how long it took, and you can also pass in an event precondition for when to actually compute this, right? And so I want to actually look at this method in a little more detail, and you'll see there's lots of index space kinds of math operations that can compute index spaces from other index spaces in lots of interesting ways, but we're just going to focus on this one for today just to try to get a feel for how it actually works in practice. But first, let's go take a look at what a sparsity map actually is. So actually, if I pull up sparsity.h, so this is the sparsity map header file. So what you'll see is that a sparsity map is a very simple handle, right? It is another one of these things that encodes a realm ID, right? And so we've looked at realm IDs in the past, right? We use IDs for representing the handles to processors and memories and all sorts of other things. And similarly, there is a ID with an encoding for sparsity maps, right? And so that's how you can pass this around by value, right? This ID is just going to encode the name of a sparsity map. And then you can refer to that ID on pretty much any node inside of your system, and Realm will know what you're talking about, right? It'll know how to go fetch the necessary metadata to actually bring that sparsity map local to the local node in order to be able to do things like iterate over all of the points inside of the sparsity map and so forth. And so in that sense, like the sparsity map is actually not particularly interesting. What we really care about is the sparsity map implementation, which is actually going to show you sort of, what are the things that actually exist inside of the sparsity map. And so, when we actually look at, I've shown you guys before how to go take a handle and look it up inside the runtime impl to give you back like a reference to the runtime, or look up inside the runtime how to get an implementation from a handle, right? So like previously we looked up like processor handles and then figured out how to get the processor implementation through the runtime using that handle. The same process applies to sparsity maps. It's almost exactly the same code, so I'm not going to go look at that here. But when you actually go dig up a sparsity map implementation, you'll get back one of these things, which is a sparsity map public impl. There's a couple of interesting methods on here. One thing that Realm kind of has to do today is that users do kind of need to, the first time you refer to a sparsity map on a remote node, you do need to call this make valid call and get back an event for when it's actually had the metadata migrated over. I've been talking with Sean about whether we should relax that and have Realm be able to do that itself without users needing to call this today. But so far it hasn't caused too much trouble. Like Legion is able to pull the sparsity map metadata over and use this event precondition as a precondition for using the sparsity map. But that's, it's a little quirk of Realm right now that could probably be cleaned up. And the isValid test whether you've already got the metadata local on your node. Interestingly, there's all sorts of things you can do, like testing whether one sparsity map overlaps with another sparsity map and so forth. And so the interesting thing here is that the sparsity maps often will contain, they can be approximate data structures. So if we look at the member variables for a sparsity map impl, the main entry here is this list of sparsity map entries. We'll talk about these other fields here in just a minute, but These sparsity map entries are what actually constitute, the data for this particular sparsity map. And if we look at sparsity map entry, its structure is right here, right? And what you see is that this is effectively a rectangle given other bounds, and then you can actually have like another hierarchical sparsity map, or you could have a bitmap representation of the data inside of this sparsity map entry. And so like we really just have a list of these things. Now I asked Sean about this, and what he said is that this field here, this ability to have hierarchical sparsity maps, is not actually something that we use in practice today. And in fact, he said you should probably ignore it, because most sparsity maps today are either lists, effectively a list of these sparsity map entries, and inside these sparsity map entries, they're either lists of rectangles or they're lists of bit masks representing the data, right? And so like, a rectangle is really good if you have a nice compact thing. If you actually do just want to have like a list of like bit masks and stuff, you can do that too. I think the most common case for Realm today is that what this is literally, in most cases, this is a rectangle. So what a sparsity map is really encoding is just a list of rectangles that contain the points for this particular sparsity map, right? Now, today, there's one important invariant that I should mention about these rectangles, because this is actually a pretty crucial thing for Realm, which is the sparsity map. Well, I should say first, these sparsity maps can exist in two states. They can exist in what we call a tight space, or a tight sparsity map, or in a loose sparsity map. And the idea of this is that it's often very easy to compute an approximation to a sparsity map. Say, for example, if you're doing something like a union or a difference or something like that, something where you're taking like a set of rectangles and subtracting another set of rectangles, right? It's often the case that you can compute an approximate version much faster than you can compute the actual precise overlapping set of rectangles, right? And so, the interesting thing that happens is that what Realm gives you back when you do something like this compute intersection is actually probably not the best example for this, because it actually is much easier to do intersections. But when you do something like unions or differences, Realm can often give you back an index space which has a sparsity map which is not tight yet. And so that's what this approximate stuff is here, right? Effectively, it's saying that the entries in this sparsity map are just an approximation of like what the actual sparsity map really is, right? And Realm is still off computing the real thing in the background, but you've gotten at least an upper bound on what data is in the sparsity map. I should say that this upper bound is it's effectively sound, but it's not precise. And what that means is that you've at least got, if a point will end up being in the eventual tight representation, the actual precise computation, then it will also be in the approximation. But what it is not is precise, right? So there are some points that may appear in the approximation, which do not ultimately end up appearing in the final computation, right? So it's always an upper bound and not like a lower bound or anything like that. And importantly, what that means is that if you actually come back here and look at this at the index space class here, there is a method here called Tighten. And what this does is effectively it takes an index space, right? It's a method on the index space, right? And if you have a sparsity map and you set precise equals true, this will actually compute the precise sparsity map, effectively from an index space that already has an existing sparsity map that's an approximation of what's actually in the resulting computation that generates this index space. So effectively it's up, and in the process that will also tighten this bounds, by the way, right? So this bounds might also be a part of an upper bound on the sparsity map, and as you tighten the sparsity map, you'll also tighten this bounds, such that you'll actually get like a perfectly precise, if you pass precise equals true here, get a sparsity map that exactly represents the points that are in the computed set, right? And so what that allows clients to do is they can actually effectively do deferred computations with index spaces, where they can get an upper bound on some complex index space math, and then later, when they actually need the precise result, then they can tighten the screws and actually get back the actual precise set. So when you look
But
at
you
What's
don't
an
get an
example
event
of
back.
something in Legion that does this? Because I mean, Legion's trying to be pretty precise.
well, that's what
Yeah,
Legion does this when it needs to. So Legion will leave index spaces in sort of their approximate form until it actually needs a precise result. So like when you do a dependent partitioning operation, Legion doesn't immediately tighten all the index spaces, right? As it starts to need things, then it will start to tighten index spaces to actually do precise computation.
And this is not done through events, like a
So
minute
that's
tighten
yeah. So
operation.
that's I mean it's actually interesting. This Titan doesn't actually return a like doesn't it can't be done in a deferred way. And I think we'll need to check with this, but I believe that I remember Sean telling me that effectively the reason for this is that if you really do need the tight index space, you actually want the result right now. And so like it's sort of an inline immediate computation to actually do this tightening at the moment. So Legion actually runs this in like a background meta task to actually do this tightening process when we need it, but and kind of defer it that way. But for like I would need to get clarification on Sean on why tighten is an immediate operation that returns you an index space, and this index space is tight by the time you get the return from this call. Did I answer everybody's question?
Yeah, it's interesting that you had to do the deferred. You had to build the deferred Titan yourself.
I do, and it's debatable. Like I can understand some of Sean's logic here for designing this way. But yeah, I usually like when you do Titan, you do kind of need the results pretty soon. It's not something that so Legion actually if I do this precisely, what Legion is actually doing, Legion actually will preemptively tighten things, but do it in a deferred way, with the anticipation that we will need things tightened eventually. But we don't tighten inline as soon as we compute an index space, is the way I should say it.
Makes sense.
Yeah. Okay. So when you think of a sparsity map, the thing I want you to have in your head is really what it represents today is a list of rectangles. And importantly, there's an important property of these set of rectangles inside of a sparsity map, and that is that those rectangles are non-overlapping with each other, right? So like each point in a sparsity map is represented in exactly one rectangle. So effectively, this is like a covering. It's like effectively a sparsity map is like a covering of the points in the index space, right? In n dimensions, right? And in really bad cases, right? Like if your index space were literally a bunch of individual points that like were completely isolated from each other, right? That's probably the only case where you don't want this list of rectangles, right? That's where you actually probably do want one of these hierarchical bitmaps, because right, effectively you've got points, like if you represented everything as points, you've effectively be doubling the representation in memory of what you actually need, because you'd have rectangles representing points and you're storing the same point in the rectangle both for the high and the low value, right? And so the only place where you really see this hierarchical bitmap be used is in the case where like you've actually got a really sparse index space where there's literally no neighboring points for any other point, right? Or very few. Right, and there's some heuristics for kind of switching between the representation of like, do you use lists of rectangles or do you use hierarchical bitmaps? But I would say the most common case is that most applications and clients actually do have groups of rectangles of points, right? Like their sparsity is structured. It's not so sparse that things actually end up getting really out of line there, and having to switch to the hierarchical bitmaps representation. Okay. So I showed you this is the sparsity map public impl, right? There's actually like an internal version of the sparsity map implementation as well. And well, actually, here's actually the implementation of sparsity map. This is sparsity map impl on the inside. Okay, yeah. So there is a sparsity map impl inside of Realm, right? And notice that this one inherits from public sparsity map impl. And this is the one, you'll notice this one is actually in a subfolder in the Realm directory. It's actually in this dependent partitioning dep part, as we call it, subdirectory. And you're going to find a lot of stuff dealing with index spaces shows up in this particular subdirectory, and we'll look at a couple of things in the subdirectory here. But effectively the internal sparsity map impl, the thing that actually gets instantiated is an instance of the public interface, right? But there's additional methods on here to actually do things like computing things on sparsity maps. And so just to set things up a little bit before I dive into how we actually compute something that actually generates a new sparsity map, right? The way to think of these sparsity map impls is, the nice thing about them is that they are immutable once you compute them, right? So you effectively, a sparsity map is in one of two states. Either it's not ready yet, or and it's still having things added to its data structure. It's still being computed, or it's been computed, and you're actually it's ready to be used by other things, right? And so one thing that happens is like you can see there's some methods here for contributing things to the sparsity map. That happens in the state where the sparsity map is still being ready, still being computed and being made ready, right? And in the process of that happening, you can also add things like add waiters, things that are going to consume the sparsity map and do things with it once it's actually ready, right? And effectively, it's in this sort of like there are these two states, and as it transitions from the first state to the second state of being ready, right, that will then wake up all the waiters and things that are needing it to compute other downstream things from this particular sparsity map. So just to prepare you, like when we go to look at how to compute an intersection or union or something like that, what we're going to do is make a new sparsity map implementation to represent the results. Right, we're going to contribute some stuff to it, and then when we're done, we're gonna effectively, when we hit this count, the maximum count of contributions, then the sparsity map will become ready, and then things that are downstream from it can actually start to consume it, and actually use the sparsity map to go off and compute further things with it, right? Yeah, I was saying, and I should point out, here's the finalize method for marking when it's actually ready. And you can see there's all sorts of representation or state for storing stuff like, how many waiters do we have? Are there waiters on remote nodes? Who else knows about this sparsity map and that kind of thing. But I do want to emphasize a sparsity map is something that is immutable once it's computed, right? So effectively, it gets mutated up to the point where it's done being computed and it's finalized, and then once it's been computed, then it's immutable. It does not change the set of rectangles inside of that sparsity map. We'll always be computing new sparsity map IDs, as needed on the fly when we actually do computations on index spaces. Okay. So let's actually take a step back here, and let's actually look at how we actually compute something like an intersection between two sparsity maps. And actually, I might pivot here just a little bit. Let's actually do compute union, because it's pretty much the same thing, but it's less. Intersections are actually kind of trivial to compute, right? And so unions are much more challenging and actually more likely to generate a sparsity map in practice. And so that can actually make things a little more interesting to us, and more likely that, like, when you actually look at this code in practice, you'll probably see it actually making a sparsity map if you do something like a union of two index spaces. Okay, so this is a static method on an index space. It takes two index spaces, right? Gives you back a new index space result. You can pass in profiling requests to get performance analysis for how long this operation took. You can pass an event for actually before you can actually launch this thing. Like, so for example, if one of these index spaces were from a remote node, and you had to call make ready on the sparsity map to make sure that it was valid over here, you could pass in those events as preconditions into this compute union call to make sure that you're chaining it properly. So if we come over here, search for compute union. So you'll notice the compute union is just a special case doing a set of things. So Realm just turns around and makes vectors of size 1, and calls the vector version of compute unions. So if we search for compute unions, right, there's one here. And this is another particular special case where you've got effectively one index space that you're computing unions against all of the other ones, right? So it's effectively like for those of you familiar with NumPy, it's kind of like a broadcasting. You're going to test this one against all the ones in this vector and get back a set of unions for all of these things. This is another one that just reverses the arguments. And so these are all the compute unions here, but it's calling this third this other version of compute unions here, which is not actually represented in this index space inline file. And so you might be wondering where you're going to find that. You're actually going to find that over here in the depart branch in the set ops file. And set ops stands for set operations, right? So effectively, you can think of index spaces as just a set of points, right? And so what we're doing is set arithmetic on those index spaces. We're doing unions and intersections and differences and stuff like that. And so if I search for compute unions, oh, I might be in the wrong file. Let's see, is it over here? Nope, I thought it was over here. It actually might be over here in, actually not this one. This is compute, or this is setops.cc. So I think it's over here in, nope. I wonder if it's in setops.inline. No. Let's see. I thought I had this one in the right place. Go into depart. I wonder if it's in Sparsity impl. It might be over here. Nope. Apologize. Gonna have to track down where exactly this setops. I thought it was in, maybe, is it in here? Here it is. Okay. So, here's the actual implementation of compute unions for an index space, right? With two vectors that you're going to zip together and give you back, a new set of index space results, that are the union of, for the ith entry in here and the ith entry in here, we're going to give you back the union of those two index spaces and the ith results over here. One thing before I dive into this function, you'll notice that this function is templated. It's templated on the number of dimensions in the index space and the coordinate type of this index space. But this implementation is actually inside of Realm in a CC file, right? And so you might be asking, like, well, if the client actually instantiates index space, compute unions, with some particular coordinate or dimensionality and coordinate type, how do we know how to get this template instantiated? Well, Realm has a sort of default set of instantiations of these templates that it does, right? So you sort of specify build time, what's the max number of dimensions that Realm is going to support. And there's also a list which actually says, what are the types that actually can be instantiated for these coordinate types on this index space that Realm will sort of pre-populate or pre-instantiate all the templates for. Let's see if I can actually find that. It's a little digression here, but I think it's actually probably worth it. Let's see here. Pop up. Is it install per here? So this is all the template stuff for doing the instantiation. Lots of macros and stuff. But I think there's actually a list of types somewhere that actually say what the coordinate types are. I might need to dig this one up later because
it's part of the build system.
It's not in the build system. So I know it's so dimensionality definitely is, right? So the build systems, both the make and the CMake builds, right, specify a max dimensionality to instantiate.
Well, we actually generate source files in the build system.
I understand. We build realm config.h, but it doesn't actually instantiate this particular thing. At least not. I mean, I'm pretty sure that it doesn't instantiate the depart list of types for the coordinate types. I think there's 3 things in the coordinate type list right now. Yeah, I will need to look this one up later. But I'm almost positive that the set of default coordinate types that Realm instantiates templates for is not is not.
Which file are you looking for?
What's that?
Which file are you looking for?
I don't know. I'm looking for the depart type list that actually specifies the list of types. That actually represent, all the coordinate types that we pre-instantiate stuff for.
So, I mean, I see in the build, it looks like it's taking image, pre-image, and by field, and creating the special instantiated versions of those.
Right, but where's the list of types for the coordinate types? That's what I'm looking for.
That I don't see here.
Right, yeah, I'm pretty sure that is hard-coded in here somewhere. And I will need to dig it up and share it with you guys later. Okay, but effectively, there's 3 coordinate types that Realm pre-instantiates things. I think it's like int, unsigned, and long, I believe. But I will need to dig that part up. Maybe if we have time at the end of the meeting, I'll go try and track that down. Okay. So Realm will pre-instantiate these templates in all of the pretty much every file inside of depart has some pre-instantiation code that will instantiate all the templates for some default, coordinate types and dimensionalities that, that are specified at build time. And that way you don't have to worry about like linking problems here with with things. But if the user does use like a coordinate type that we're not pre-instantiating templates for, well then we might have some link errors and have to deal with that. Okay. So how does this function actually work? Well, so we're going to loop over all the entries, right? We're zipping together all these things. So this is the loop over entries, right? The first thing we do is we handle any kinds of special cases, right? So if either of our left or our right, entry is an empty index space, right? Well, then the union is trivial, right? You can effectively assign the results to the other index space and you're done. If you have, if your index space is dense, right, and it contains the bounds of the other one, then your union is immediately done, right? And so you can set results and return right away, right? And in particular, like if you notice that you have the same sparsity maps in both the left and the right hand side, right? And your bounding rectangles are then you can compute the union bounding rectangle, and then you can make a new index space from that, right? And only in the case where, so effectively Realm has all sorts of fast cases to handle things where like index spaces are rectangles and they do things that are pretty nice with each other, and you don't need to actually make a sparsity map, right? But in the case where you actually do need to compute stuff, right, we actually are going to need to compute an actual like union here, right? Then what we're going to need to do is make one of these union operations. And we'll look at where this comes from here. But this is going to be another kind of Realm operation that's actually going to go off and compute stuff. So, and when I say operation, that should mean something to you. It's the same base class as like a task base class. Pretty much anything is an operation that can be like canceled or poisoned and stuff like that. So this is going to inherit from that base operation class. Right, and we get a finish event for when we're going to need that. We just need to do that the first time we need to make one of these things. So this operation is going to compute, the unions for any of the things in here that actually need to do a computation. Okay. So, and at the end here, if we've actually if we have an operation, right, that actually is going to go off and compute, a particular union operation that's going to, we add this union computation to say we're going to union, this left and this right hand side index spaces. And then we get down here, if we have an operation, we're going to launch it. Otherwise, if we don't actually have to launch an operation and the user actually asked for profiling information, right, we still do some profiling just to record, how long did we spend in this function doing the simple analysis for doing like basic rectangle intersection and stuff like that, right? And then we can return the event for when we actually are done with this computation. Now, there's one interesting thing that I want to comment on here before we go look at this this union operation that we created here. So one interesting thing that you may notice here is like in this particular case where the sparsity map is the same and we give back a new index space, right, with the same sparsity map and some new bounds on that union there, right? Like one thing that's really interesting about that is that this actually makes it, kind of hard for the client to actually know, when it's safe to delete sparsity maps, right? So one thing that I guess I should have said over here, the sparsity map class actually does have a destroy method on it. Let's see, where is it? Or actually, no, it's not sparsity map. The index space class actually has a destroy method on it. So if I come back up here to the top of index space, there is a destroy method on an index space, right? And that will actually clean up the sparsity map of this index space if it exists, right? But that actually, it's really hard for clients to know when it's actually safe to destroy an index space if you can have optimizations like the one that we just saw. Where's my code? I've got too many tabs open. Here we are. If you reuse sparsity maps here, right? So there's an obvious conundrum here for clients to know when it's safe to actually destroy an index space and actually clean up the resources associated with sparsity map. And as a result, this is actually something that's a little undefined in Realm right now. And it's actually an open issue that needs to be resolved, is that, if I actually showed you the implementation of that index-based destroy method, it's actually not doing anything right now. And so sparsity maps are not ever cleaned up today. So technically there is kind of like a little memory leak in Realm at the moment, in the sense that, clients can call destroy on index bases, but they don't actually clean up the sparsity maps. Sparsity maps kind of live forever at the moment today. I mean, they do get cleaned up at the very end of the run, but nothing cleans them up in the middle when they may already have been deleted, because clients don't know, you might have multiple index bases that refer to the same sparsity map. And so it's TBD, Sean has said he has a plan for actually, telling clients when it's safe, like when they get a new sparsity map versus when they actually are reusing an existing one. And that way they know whether they're responsible for deleting the resulting, computation that comes out of, or destroying the index base that comes out of like one of these new like compute unions computations. So TBD on getting that fixed. But today the answer is just that sparsity maps are not actually destroyed. They live forever at the moment. Okay, so let's actually dive into this union operation and take a look at where that actually, what that is. Okay, the setups. Here's setups.h. Here's our union operation. Okay, so this is a union operation, right? You can see you can add unions. There's two different kinds of unions. You can either be unioning pairwise two things, or you can be unioning a vector of things together. We'll focus more on this one because it's the one that we're looking at the moment. You can go look at this one here. The base class for this is a partitioning operation. So just let's take a look at partitioning. Yeah, cannot spell. Why am I not? I thought the class partitioning op was in here. Maybe it is in a different file. It might actually be in partitions.h. I think that's probably the case. Did I pull up partitions.h? I don't think that I did. Pull it up here. Here we go. Partitioning. There we go. Okay. So as I mentioned before, this is a base, the base class for a partitioning operation is a base operation. So this has all the same methods as, a normal operation. It can be, poisoned and canceled and all sorts of stuff. But it also has, an execute method for actually being invoked and stuff like that, and launching itself. So this is just the base class for this, but I did want you to see that it is an instance of the base operation class, and that also handles stuff like profiling requests and triggering the finish event for this operation when it's actually done running, and so forth. Okay, so set ops. Let's see. We want to look at compute or union operation. It's a template. That's right. Let's look for add union. There we go. Okay. So when you add, here's the add union method, adding this into this this new union operation, right? Right. So the first thing that we do is effectively, we need to check to see who's actually going to perform this this particular computation and where the sparsity map is going to live for this computed union operation, right? There's some heuristics in here, right? So there's an open question here as to like, where is the obviously best place to put this new sparsity map that we're computing, right? And in particular, like, do we put it on this local node where we're actually, where this compute union operation was invoked, or are we going to put it somewhere else, right? And it's not obvious because, the sparsity maps for these two index spaces might actually live on two remote nodes from the node where we actually had, the union computation being performed, right? And so Realm has some heuristics here for deciding, effectively if one of these things is dense, right, we're probably going to put the sparsity map on the resulting node where the sparsity map for the other sparse index space input is, right? And if not, right, well then we're probably going to do it on probably either our local node or one of the remote nodes, depending on what the sparsity actually looks like and stuff. So there's heuristics here, and I'm not going to go through all the combinations of them, but effectively Realm is deciding here, where to put the resulting sparsity map for this union computation. And it's not always immediately on the node where you do the compute union call, because like if both sparsity maps are remote from here, it's probably not the best answer to be doing that remotely, right? So, and once you've actually decided where you're going to put it, right, then you can actually get the name of a sparsity map that you're going to contribute to, right, and actually sort of set that as the place where you can actually make it a sparsity map, and this is going to be the thing that we contribute to as part of our computation, right? And so, and then here we fill in the inputs and outputs for our union operation, and we save them for later. Similarly, there's this other add union operation, which is another variation on this, but a lot of the logic is pretty similar, right? And then we get the execute call, right? So once our event precondition has triggered, right, then this union operation is going to be executed, right? So we get the call back, coming back from this operation once our event precondition is met. I've shown you guys that logic before, so you know how to go add event, like effectively adding event waiters and stuff like that. Like that'll end up triggering this union operation and executing it once the event precondition is ready. Or if it's been poisoned, this thing will get poisoned. But in the case where it's not poisoned, right, we come in here, right? And so what we're going to do here is we're going to actually, effectively look at, our sparsity map implementer. We're going to say, how many contributions are we expecting on this particular sparsity map? There's only going to be one because we're just doing one union operation here. So there's going to be one contribution from this micro-op, and I'll talk about what that is here in a minute. There's only going to be one contribution, so that sparsity map will know that it will be ready as soon as it's had its contribution made to it to say, here's your set of rectangles for this particular computation. One important thing that this code is actually hiding is like if this sparsity map is actually going to be on a remote node, this can actually trigger an active message to send this contribution count to the sparsity map on the remote node. So just keep that in mind, like whenever you look at this, like the sparsity map may actually be actually being stored on a remote node from where we're actually like having this control logic run. Okay, so a union, we're going to turn around and call make one of these union micro-ops. And you're wondering, okay, we're already in a union operation. Why do we need one of these union micro-ops? Well, it turns out that these micro-ops are actually a very useful primitive and abstraction for doing other kinds of dependent partition computations. So in particular, when we do things like images and pre-images and stuff, we also need to do things like unions. And so what you're going to see is that, and we'll look at dependent partitioning operations later, but effectively, Realm is using the same infrastructure here for doing this basic union operation as we're going to use for doing more complicated dependent partitioning computations later. So this union micro-op, let's actually take a look at that. Let's see here. Here's our union micro-op. So you'll notice that this is an instance of a partitioning micro-op. All right, so this is a sort of a sub-computation. This is not a normal operation in the sense that it is a base inheritor of the operation class. This is very specific to partitioning. If I look up partitioning micro-op, let's see. Here it is. Right, so this is its own base class. And this is sort of a generic kind of thing that's going to be used for actually doing computations for dependent partitioning. And in particular, what they will end up doing is when they actually enqueue themselves. So if we come back here and actually look at this, right? So when you actually dispatch a micro-op, what that's going to do is put this micro-op into a work queue that will then be registered with the background worker threads. And so let's see if I can actually, so effectively there is a generic partitioning queue, which, you can add micro-ops to, right? So actually, is this the right one? This is probably not the right one. This is actually the partitioning operation. I want the micro-op one. Let's see. Make sure I get the right one here. Right, so you can make an async micro-op from a partitioning micro-op. Sorry, I forgot how this actually works since I studied it earlier today. We got into the details. I may have to come back and explain this part later. But the idea is that this dispatch method here is going to enqueue this in a queue of micro-ops that will actually be able to run effectively by the background worker threads for Realm whenever it's whenever they get around to it, right? So the background worker threads have a queue of stuff to do, right? And they'll come around and actually run these micro ops for actually doing these operations. So let me actually let's actually take a look at union micro op here. Here's all the template stuff. Okay. So here's our union micro op class, right? And we're storing our, we have our Sparsity map output here. Let's see. And let me remind myself, pretty sure I need to find the place where this actually does the union. And I have forgotten where that went to.
So these operations are sharing resources with like advancing the network?
Yes. So like effectively Realm, like they all go into the background work, queue effectively. And really there's like several queues, and what the background worker threads do is they service each of the queues. We haven't actually looked at this part yet, right? They service each of the queues and give them sort of a timeout, right? They give them like a time slice. Like we recommend that you run for, I think the default time slice is like a few hundred microseconds, right? And then report back to us and give us control back so we can go off and do something else, right? And service a different queue, right? And so these like the micro ops and stuff are designed to be pretty lightweight things that do a very small amount of work and then give control back to the background worker thread so they can go off and service something else. And that keeps liveness, moving forward. But yes, like if you had like an extremely long micro op or something that consumed a huge amount of time without giving control back, which we haven't actually looked at yet, right? That could like stall out your message handling and stuff like that. Okay. So let's see. Here's our union micro op execute class, right? So the way that this is going to work, the way this union micro op is going to work, we're going to make one of these dense rectangle list things. And what we're going to do, right, we're effectively going to populate this with the entries from both of the two. The way to compute a union is effectively you merge together the two lists of rectangles from each of the sparsity maps in each of the entries of this union, right? So this dense rectangle list, if we actually go look at it, I think it's over here in partitions.h. Actually, it might be in its own file. Yeah, I think this is in says its own header file here. Yep, rectlist.h. So this dense rectangle list, right, is effectively a list of rectangles. And if you read the comment here, it's actually very important, right? So this dense rectangle list does not actually do the deduplication of all the entries inside of this inside of this list, right? So remember I told you that each sparsity map should have exactly one rectangle to represent a specific point inside of it. Well, this dense rectangle list is not doing that. It's just accumulating all of the things inside of or in a list of rectangles. So if we pop back here, so we made one of these dense rectangle lists, and we're going to call it populate bit masks. If we come up here, populate bit masks was up here. Here's our populate bit mask. It's templated on the argument. So you could pass in a dense rectangle list here. You could also, there are other things that you can pass in here. So there are other things here like hybrid rectangle lists. You could also imagine passing in like you can also pass in like one of these coverage counters to count how many things there are. I think Sean has also toyed around with passing in like actual bit masks here to actually represent literally the bits for points that are actually stored in the list instead of like the actual sets of rectangles. So that's the reason that this class or this method here, populate bit masks, is templated. This block of code is commented out. You can ask. There's a fast case for like for 1D stuff. Let's see, where was the end of the commented out code? We have commented out code inside of commented out code, which is fun. Okay, so here's the actual implementation, right? So it iterates over, all the entries and the inputs, right? If it's dense, you can just add the rectangle. If it's a sparse index-based input, right, then we get the sparsity map. We iterate over all the entries and we add them. We do the intersection with the bounds to make sure that they're still inside of the bounds of the rectangle, right? And then we add them into the bit mask. So this bit mask, effectively this dense rectangle list, which is the bit mask that was passed in here, by the end of here just has a list of all the rectangles without having deduplicated them, right? And then, we can actually contribute that to the sparsity map. So you can do this contribute dense rectangle list to the sparse map, or to the sparsity map. And when you do that, that's what's actually going to go ahead and, populate that sparsity map with its values. And because it knows it's only expecting one, sort of contributor, right, it'll know that essentially as soon as you're done contributing to that sparsity map, then it's actually ready to actually be consumed and be used by anything that's looking to compute things from the sparsity map that we're computing here. So let's actually take a look at this contribute dense rectangle list. Is it in this method? I don't think so. I think it's in the it's actually in the sparsity map impl here. Yeah, here it is. So here is the dense or contribute dense rectangle list, right? And the first thing you'll notice here is that there's a check here to say, are we the owner of the sparsity map? If not, package up all the data inside of this rectangle list and ship that over to the remote node where the actual owner sparsity map is on, for contributing to the sparsity map, right? And so we send off our active message and then we're done, right? So that's the case where we're actually contributing to a sparsity map on a remote node. Otherwise, we call contribute raw recs, right? And so here's the contribute raw rectangle case. So, right, you're effectively passing in a list of rectangles, right? How many rectangles are in this set, right? There's also a way to tell the contribution here whether all these rectangles are a disjoint. So obviously in the case of the sparsity map, this is actually set to false. And I think we can actually see that over here. Yeah, so you can see effectively we're telling the sparsity map here, hey, you're gonna have to deduplicate this stuff because disjoint is set to false because we actually haven't done the deduplication between these rectangles yet. So we still need to do that over here in this contribute code. Okay. So, in the disjoint case, right, it's actually, really simple. You can just add in the new rectangles and just add them to the list of entries inside of the sparsity map implementation, right? And just accumulate them or add them in as new rectangles. No hierarchical sparsity map, no bit masks, right? There's a special case here for n equals 1 because we can do some very fast math for actually doing the interval, effectively doing overlap tests on intervals to see, to do merging between rectangles that are already represented in the list, along with any rectangles that we're adding from the new list, right? So this math is, tedious, but not terribly difficult logic-wise to actually go and work through. The more interesting cases in n dimensions, right? So in n dimensions, you actually have to test rectangles against each other to see if they partially overlap with each other, right? And so we have to iterate through all of the entries, right? And test for, or for each rectangle that we're adding, right? We pop it off the list, right? And now we're going to start, or we make we make a list of all the rectangles, right? That are inputs, right? And then we're going to keep iterating until we're done because as we try to add new things, they might split old rectangles into new ones that need to be added back in, right? And so we iterate over entries looking for interferences. And if they do interfere, then we have to handle all the interesting cases, right? So, if the rectangle already contains the old one, right, we can absorb it and keep going, right? If we can merge with another one, we can do that. And then you get into the really nasty cases where you have partial overlaps and you've got to split into, all the different combinations of sub-rectangles above and below and stuff like that. And then they get added back onto this list to add, and you keep iterating until you've actually completed adding new things to the list, right? And if you get all the way down here, you made it without actually interfering with anything, you can add that, right? And then, so you do this until you've finished adding all the rectangles to the list for the sparsity map, right? And then down here at the bottom, this is the logic to actually check, effectively, have we seen all of our contributors, right? Have we gotten all of our contributions that we were looking for? And if so, we can go ahead and wake up all of our waiters and stuff like that and say, and call this finalize method to mark that we're effectively ready to be consumed as a sparsity map, and we've got all of our rectangles and we're ready to go. So, so we're almost out of time. This code is, the logic for it is pretty straightforward. There's lots of details. Lots of the geometry here is kind of interesting, and I didn't actually go into the details of that, so definitely take a look at that if you're curious for handling all the cases. And, as you go back and look at all of these methods that, exist on index spaces for doing things like creating new index spaces and stuff in lots of different ways, they're all going to follow this logic, right? We're going to look at some of the dependent partitioning ones because they're a little more interesting at a later date. But pretty much everything in here that computes an index space, by making a sparsity map will do all the same things that we looked at here today. And there will be different cases for intersections and differences and stuff like that. But the general flow of how the control executes for actually, computing sparsity maps for index spaces is all pretty much the same. And always remember that there's like fast paths for things where like index spaces are just rectangles and don't actually have sparsity maps, and realize that might actually not go through a lot of the code that we go through today. You only pay for this stuff if you actually are, needing to make sparsity maps and stuff like that. So with that, I think I'm done for today. I'm going to open up for questions for anyone who has them.
Yeah, so I had a question, generally just about the philosophy of this design.
Mm-hmm.
Like, I mean, I guess I'm wondering, like, clearly having all this index space logic, inside of Realm makes the implementation of Legion easier. But at least, like, the presentation that, always get as someone who's learning Legion is that a lot of this stuff, index spaces in particular, are all like, part of the Legion programming model. So, like, how did you guys end up deciding to put all of this into Realm, and like, what are the benefits and trade-offs there of doing that?
Well, so the value of putting the reason for Realm to understand the geometry is pretty straightforward, right? Like, these index spaces are going to show up everywhere inside of Realm, both in terms of like how we make instances and how you issue copies, right? And those kinds of, and how you and that's pretty much data movement and data layout and stuff like that. And so Realm needs to understand this geometry in order to be able to do those kinds of things efficiently, right? And that includes understanding the sparsity of instance layouts and sparsity of copies and stuff like that, right? So Realm has to have this logic in order to be able to do that kind of reasoning. One thing that's worth pointing out is that Legion's index spaces are actually quite different than Realm's index spaces, right? Like, Legion's index spaces are just names, right? These index spaces in Legion are actually what Legion calls an index space a domain, right? So Legion distinguishes between values and names a little bit more clearly, right? So effectively, like an index space in Realm here has both a value and a name internally, right? It has both the bounds, which are a value, and then also a potential name for a sparsity map, which is actually a name for a thing that doesn't actually contain any data, or actually represents the actual data for this thing, right? And Legion index space is just a name for a set of points, right? And then if you want the domain for that index space, you kind of have to ask Legion for that separately. So there are some distinctions between how Legion and Realm think about index spaces. But I think it's actually crucial that Realm be aware of the geometry of these index spaces, so that when you do things like copies or instance layouts, it knows how to translate, like if I ask for a copy, from one instance to another, and I only want to move some of the points between those two instances, and those instances have each have their own layout, right? Then Realm needs to understand the geometry of those things with their own index spaces, so they can match up the points and know like which data associated with which point are going to move from instance A to instance B and so forth. Did I answer the question?
Yeah, makes sense.
I have a question about sparsity map immutability, beyond creation and validation.
Yeah.
So there are situations during a simulation where parts of the domain just go away. Like, for example, in graph contraction,
Mm-hmm. Yep.
Sets of nodes just disappear and contract into one.
Yep.
So how do you, if the sparsity map doesn't go away ever, then how do you notify?
Yeah. Well, like I said, I think there are two separate issues there. So, like, the first one is sort of a logical one, and the second one is the physical memory part of it, right? So one thing that we actually do encourage people to do, like, these index spaces, right? They are, and sparsity maps are immutable. So you do kind of want to make ones that are big enough that they're going to represent your simulation. But if you're going to contract, there's really no cost to you using only like a subset of points inside the index space. Like because index spaces don't correspond directly to instances and memory layouts and stuff, you can always like take an index space and then compute a subset of it and then use that to make the actual like instance layouts for data and stuff, right? And so you don't always have to use the full index space. So in the case where your simulation like contracts and uses like fewer points than it initially started out with, you can always shrink down your index spaces, right? Now and only use a subset of the points. the more interesting question of like, cleaning up sparsity maps when they're no longer needed and actually having this destroy method actually do something, that's something that does have to be resolved, because I think it's not tenable in the long run to actually continue just leaking sparsity maps and letting them live forever. And the important thing is that like effectively what the user needs is sort of an understanding of like when you call something like compute union, is it safe to actually, is that a new sparsity map, or is that just a new reference to an old sparsity map that I now need to like, be aware of those differences and stuff. And so, Sean has said he's going to document exactly what the scenarios are for like, compute union and stuff. Like do I get back a new sparsity map or not, and how do I tell, and when do I need to check for duplication and stuff as the client, so that I know that it's safe to actually delete sparsity maps and stuff. Legion actually does a pretty good job of this today, but it's still pretty it's not actually doing anything because Realm doesn't actually do anything.
So that is essentially an attempt to do some sort of garbage collection.
Yeah. So and I think, the unfortunate thing is like, so you don't have to collect events in Realm, right? Because events just kind of like, with the generational event data structure, they can recycle themselves, or not recycle, but there's very little cost to not collecting events in Realm with generational events. But with sparsity maps, they're big, complicated data structures, and so when you're done using them, you kind of want to know it. And it's really hard to do distributed reference counting, inside of Realm on these things, right? Especially if users are passing or can serialize up like an index-based handle, it's a trivially copyable type, so that like, we can't do reference counting and stuff on the sparsity map itself directly. So we kind of need the user to tell us when it's safe to delete it.
Yeah, I can envision a CFD simulation when maybe at some point the valve closes and all of a sudden 3/4 of your domain goes away.
Yep.
Because,
Yeah, exactly. And so you would definitely want to clean those things up. And I think it is something that we do need to resolve in Realm is actually how to actually collect those sparsity maps and make it so that the destroy operation actually does something. So definitely agree.
Thank you.
Okay. All right. No more questions. Happy to close for today and talk to you guys next week on a Legion week.